This is the 10th episode in a series covering the design and construction of a clock for my relay computer. In the last episode, I prototyped the primary relay clock design, but now it's time to look at an alternative secondary design which uses a very different approach to creating the clock signal. Let's have a recap first though on why I've got two designs on the go rather than just one. And looking all the way back to episode 2, I'd actually got 4 potential options for creating my relay clock. My requirements were that chiefly it needs to produce a well-formed square wave at 6 Hz, bonus points if it can output a range of frequencies. I also need to manually start and stop the clock when required. And when I do stop the clock, the signal being output should rest in the off 0 volts position so that I can manually operate the clock line. This will be used in debugging scenarios or if I just want to manually clock an instruction through. There should also be a halt instruction that allows a program to stop the clock and pause execution. Lastly, I'd like to get a whiff of authenticity into the clock and keep the electromechanical theme going. As it turned out, all 4 options fitted the criteria pretty well, but the relay-based clock was, of course, the most authentic, so absolutely made the final cut. The other option I really liked was having a clock based on a crystal oscillator. This will give me the most flexibility in terms of range of frequencies and will be both accurate and reliable. With the relay-based clock design all done with then, let's take a look again, at a higher level, of how a crystal oscillator works. And when thinking about designing a clock circuit, it's hard not to consider how something like my humble IKEA clock here pulls off its job of maintaining a very good 1 Hz signal. These clocks, like most cheap ones, have a quartz crystal at their heart which vibrates at 32.768 kHz. You may have spotted that that's a power of 2, and so if you could keep dividing the signal down by 2, you'd eventually get to 1 Hz. What do I mean by divide by 2? Well, you can run the clock signal through something called a flip-flop, which will change state on every rising pulse coming in. This has the effect that it changes state half as often as the input, effectively giving you an output signal which is half the frequency. In other words, it's divided the frequency by 2. You can chain these flip-flops together to keep dividing by 2 until you get the frequency you want. This is perfect for what I need here. When flip-flops are chained together like this, they effectively form a binary ripple counter, because each output is representing the values 1, 2, 4, 8 and so on. Each rising clock signal on the input will increment the overall binary value present by 1. Likewise, if you look at this diagram another way, the 1 slot is changing half as fast as the clock, and the 2 slot is changing a quarter. It's dividing the clock by 2 in stages. As you might imagine, there's chips available that hold all this functionality in a single package, and all I do is use them to take it down to the slowest frequency I might want to use, which, let's say, could be half a hertz or something similar. Given these ripple counters expose all the intermediate frequencies, I can also take an 8-channel data select chip to pick one of the 8 inputs given a 3-bit selector value. This is a nice tidy solution and gives me a range of speeds, all with excellent accuracy. Not that my computer particularly needs the accuracy, but there we go. And being honest, this design is neither unique nor new to the computer. This is exactly how the little temporary timing board works that I've had in my computer for some time. I adjust the clock's frequency via the dip switches, which then picks off the appropriate frequency from the ripple counters. It's this temporary board design that I'll explain a little bit more now and then incorporate it into the overall clock card design. So in terms of overall design, let's take what I've covered so far and show that as a high-level block diagram. I'll need an oscillator that will produce a square clock signal at 32.768 kHz. That will then be fed into a binary ripple counter which will progressively divide the frequency by 2. From there, I'll tap off the clock frequencies I'm interested in, and then all that remains is to pick one of those off and pass it through to the rest of the computer. Right then, let's take a closer look at the first block, the heart of this clock design, the crystal oscillator. And to explain what a crystal oscillator is and how it works, I probably need to step back a bit and talk about oscillator circuits in general. Now I'll try and keep out of the maths and detail on this one, as that could make an episode in its own right. But effectively an oscillator is a circuit that can produce a periodic, oscillating electronic signal. Typically that will be a sine wave, and so another way of looking at it is an oscillator converts direct current from a power supply to an alternating current. So how do I go about generating an oscillating signal? Well, unsurprisingly there's tons of options and designs available, but one of the simplest is the LC tank circuit, so named because its main components are an inductor, the L part, and a capacitor, the C part. Here's a circuit. Firstly, the capacitor is charged via the power source, like so. Once fully charged, the switch is toggled and the capacitor begins discharging through the inductive coil. As the voltage across the capacitor falls, an electromagnetic field builds up around the coil. Eventually the capacitor is completely discharged and the energy that was originally stored in the capacitor, as an electrostatic field, is now in the inductive coil. As there's no voltage left to maintain the current within the coil, the electromagnetic field begins to collapse. A back EMF is induced in the coil, which charges up the capacitor with the opposite polarity to its original charge. This continues until the electromagnetic field of the coil has collapsed completely. The energy originally introduced into the circuit has now been returned to the capacitor, which again has an electrostatic voltage potential across it, albeit the opposite polarity. The capacitor now starts to discharge again back through the coil, and the whole process is repeated. The polarity of the voltage changes as the energy is passed back and forth between the capacitor and inductor, producing a sine wave voltage. In theory, this cycling back and forth will continue forever, but in reality components aren't perfect, and energy losses occur each time, which ultimately decay the oscillations over time to zero. The longer it takes for this decay to zero, the higher quality the oscillator. Unsurprisingly, it's the values of the capacitor and inductor that determine what the frequency of the sine wave will be and how quickly the energy will be lost, although these aren't the only places energy losses can occur in the circuit. But I promised I won't get into the maths, so let's skip over that. The overall concept stands. Now you might recognise some of this circuit from the relay ring counter shown earlier in the series. Here the relay coil represents the inductor. Relay coils are, of course, designed to excel at mechanical movement rather than being a particularly efficient inductor. Nonetheless, it does have inductive characteristics, and elsewhere in the computer that back EMF generated is undesirable, and I soak it up with that reverse bias diode. Here the back EMF is desirable and used to charge the capacitor. So, I have an oscillator, but not one that lasts very long. How do I keep the sine wave going as long as I want? Well, I'll need some way of topping up the energy lost. For example, if I could just let through enough of the power supply, I can replace the energy lost and keep the oscillator going. This concept is called feedback. If energy replaced is too large, the amplitude would increase until it gets clipped by the power supply. Too little, and all it will do is just prolong the gradual decrease to zero. The simplest way of replacing this lost energy is to take part of the output from the LC tank circuit, amplify it, and then feed it back into the LC circuit again. This process can be achieved with a voltage amplifier like an op-amp or a bipolar transistor or similar. I'll skip the detail again on this one, else we'll be here all day. But again, the basic concept is I need some form of feedback to keep the oscillator running. So, why not just stick with a basic LC circuit? Well, there's a better, more precise option available, the crystal oscillator. Typically, one of the most important features of an oscillator is producing a constant frequency even under varying load conditions, temperatures and whatnot. Oscillators using a quartz crystal do this really well, which is why you'll likely find them in your digital watch or driving the CPU of your digital device. The quartz crystal in this case is typically a small thin wafer shaped like a tuning fork. When voltage is applied across the crystal, it changes shape. This is known as the piezoelectric effect. This works in reverse too, and a mechanical force applied to the crystal produces an electric charge. This piezoelectric effect produces mechanical vibrations or oscillations which can replace the standard LC tank circuit shown earlier. The physical size and thickness of the quartz wafer sets the frequency it will oscillate at, and a wide variety of frequencies are available. The quartz wafer is housed in a sealed can that looks like this, and its circuit diagram symbol looks like this. OK then, we've got our crystal, but as before I need to implement a feedback circuit to keep the oscillations going. And this circuit is known as a Pierce oscillator, named after its inventor George W. Pierce. And virtually all digital IC clock oscillators are of this type, because it can be implemented using a minimum number of components. Here, an inverter gate is used as the main amplification component, and for this example will be of a CMOS Schmitt trigger type, meaning that as the tank effect is taking place at its input, it will make a clean, decisive switch from high to low, low to high at its output. The output, of course, being at supply voltage, producing the amplification needed for the feedback. The two capacitors determine the value of the crystal's low capacitance, and are typically of equal value. If I wanted ultimate precision, I could make one of them variable and tune the circuit to an exact frequency, making up for any tolerances in the other components. The series resistor here helps limit the drive current in the crystal, and also isolates the inverter's output from the complex impedance formed by the capacitor crystal network. The inverter is initially biased into the middle of its operating region by the feedback resistor here. The exact value of this resistor isn't critical as long as it's high, 1 megohms or more. Now you might have spotted it, but the inverter effectively produces 180 degrees of phase shift, the inverse of what is at the crystal. It's the capacitor network around the crystal that provides the additional 180 degrees of shift required to match the oscillation in the crystal. The advantage of the CMOS crystal oscillator is that it will always automatically readjust itself to maintain this 360 degrees of phase shift required for oscillation. The output of this circuit is, of course, a square wave rather than the sine wave because of the inverter gate. Naturally, the maximum frequency depends on the logic gate used, that is, it must be able to switch quicker than the frequency the crystal oscillates at. Finishing off, it's good to use an additional inverter to buffer the output from the oscillator to whatever it's feeding downstream. So that's the basics of my oscillator circuit. Let's look at frequency division next. And again, to explain this one, I'll back up a bit and build up from something more basic. Let's start with some basic logic gates. We've already seen an inverter in the oscillator design, but two more worth talking about are the AND and NAND gates. Both these take two inputs and perform a logical AND and not AND respectively. Here's their truth tables. Now, taken on their own, they're not all that exciting, but as with most things, if you combine them together, you can make some more interesting things, and the NAND gate is particularly useful, as we'll see in a moment. One of the useful building blocks you can make from a NAND gate is what's known as a flip-flop. There's a whole family of these, but we'll start with a set-reset flip-flop, or SR flip-flop for short. As you might guess, this allows you to set a value and then clear it later. Here's a circuit, and you can see the output of each NAND gate feeds into the input of its neighbour. Let's work through its states, starting with the set state, which is R-high and S-low. With this, the upper NAND gate must therefore be outputting high. This feeds into the lower NAND gate alongside the high-R, giving a low output. This feeds back into the upper NAND gate, but has no impact on the output of that gate. We're now in the set state. Setting both inputs to high makes no change to the output because of the feedback into the upper gate. For the reset state, we set the R- output low. This now sets the output of the lower NAND gate to high, which feeds back to the upper NAND gate, setting its output low. This feeds back into the lower NAND gate, but again has no impact on its output. We're now in the clear state. Setting both inputs high again makes no difference to the output, and the state is maintained, as before. But note that the Q outputs are flipped from before. The only input state we can't support is having both inputs low. Here, both NAND gates feed back into each other, creating unpredictable results. We therefore consider this an unsupported state. For the same reason, the SR flip-flop starts in an indeterminate state as well, so needs either setting or clearing as required before the output can be depended on. Another problem here is that the set and reset line work with the inverse of the values you might expect. Well, I can easily fix that by adding a NOT gate in front of each, and we can make those from NAND gates too, by tying the inputs together like so. That now changes the truth table like so. Given this is a common circuit building block, it can be represented as a single block in a diagram like so. Now effectively the SR flip-flop is a data latch of sorts. In fact, you could take 8 of these and tie the reset lines together and you've pretty much got an 8-bit register. Cool, yeah? So where can I take this next? Well, here I've extended the basic SR flip-flop to make a D-type flip-flop. Here the value at input D can set or reset the state, but only when the clock line is high. The updated block symbol is shown on the right. Very quickly working through its truth table, as before, the SR flip-flop will start in some indeterminate state, so let's assume here it's in the reset state. With the D and clock line low, the SR flip-flop will hold its current state as expected. Setting D high, but keeping clock low, likewise has no effect on the SR flip-flop. However, if we now put the clock line high, then the high D input puts the flip-flop into the set mode. Finally, setting the D input low, whilst the clock line is still high, will reset the SR flip-flop. Note how it's now impossible to put the SR flip-flop into that unsupported input state, because the NAND gates in front of it block that from happening. Now this might not seem immediately all that exciting again until you combine these D-type flip-flops together. Have a whole line of them with each Q output connected to the next D input, tie all the clock lines together, and you've got a shift register, where the value at the entry D line is passed down the chain at each clock pulse. Instead of that though, I'm going to stick with a single D flip-flop, but apply some feedback. So here's a single D-type flip-flop, but let's hook the inverse Q output back into the D input. Let's see what that does to the truth table. Taking the clock line high sets the Q output. Setting clock low keeps the current output. Setting the clock line high again sets the output to low, the reverse of before. Finally, setting the clock line low again holds the current value. Notice that we're back where we started now, and if we keep toggling the clock line, this pattern will continue. Spot anything interesting in that? Well, let's show it as a clock signal over time. And here's the output. And there's the divide by 2. Chaining these modules together, outputs to inputs, will progressively divide the original input by 2, which is exactly what I'm after. Only problem I guess now is where to get all those NAND gates from. Well, like most things, I can get an integrated circuit for that, and the CMOS 4000 range is perfect for this sort of hobbyist adventuring. The 4000s operate on a wide range of voltages, including the 12 volts of my computer, and have a lot of choices available, and are cheap, cheap, cheap. Which actually always surprises me, as they're quite old designs now, and most consumer electronics have moved on to programmable chips, or completely custom ICs. Anyhow, as I say, for hobbyists like me, they're a perfect choice. Now of course there's a 4000 series option for NAND gates. In fact the 4011 has 4 of them. Shown here is what's known as a pinout, showing what's what. Great, I can put together my D flip-flops using these NAND gates, yeah? Well, there's no need, because actually of course there's a 4000 series chip for that. And it's the 4013, which contains 2 D-type flip-flops on a single chip. Note also that each flip-flop has an additional set and clear line, which sets or clears the flip-flops regardless of state or clock. Perfect. I'll have my divide by 2 circuit in no time. Well, actually the 4000 series has one of those too. And here's the 4060 binary counter, which contains a 14-stage divider. Enough to get me from 32,768 Hz right down to just 2 Hz. This isn't the only trick this chip has inside it though. There's also a built-in oscillator, which means with just a few external components I can get my crystal oscillator circuit from earlier. No additional inverters required. Internally within the chip, the output of the oscillator then feeds into the first divider stage and then ripples through the subsequent dividers, producing the frequencies thus. The reset line, marked RST on pin 12, effectively zeroes out all the divider stages, or if you're using this chip as a binary ripple counter, resets the count to 0. In this case I'll keep that tied to ground, as I never need to reset. I'm only interested in a value going high or low at the right time, although it does mean if I stop the oscillator midway through, say, a 2 Hz output, it'd pick up where it left off, giving the first pulse of half duration. Activating reset would start the time period from scratch. Now actually, as it happens, the whole circuit will be powered off when I'm not generating a clock signal, so none of this really matters. Now you might have noticed a problem with this chip. Some of the divider stage outputs aren't available from outside of the chip. The first three, 16384, 8192 and 4096 Hz, I'm not fussed about, as my computer couldn't hope to operate at those sorts of speeds. But not having the 16 Hz output is unfortunate. I'd also like to get clock frequencies lower than 2 Hz too, but actually I can work around this. Before I do though, here's the oscillator circuit using the 4060. As before, I've got the 32,768 Hz crystal, along with the 1 megaohms biasing resistor. To limit the drive current through the crystal, I've selected a 2.2 kilo ohm resistor. And that just leaves the capacitors, which are 33 picofarads each. Now again, I could have used a variable capacitor instead for one of these, if I really wanted to tune the frequency in, but given I'm dividing it down so much and don't need absolute precision, this will be fine as it is. Right, back to that missing 16 Hz output. Now I can just hook another ripple counter off the back of the 4060 of course to continue the division. Here I'll use a CMOS 4024, which is a 7-stage ripple counter. And if I take its clock input from the 32 Hz output on the 4060, that'll give me outputs all the way down to 1/4 of a Hz. And it fills in for the missing 16 Hz output on the 4062. So let's update the circuit diagram. And as with the 4060, I ground the reset pin to keep it low and inactive. And that's the oscillator and divider complete. So next let's move on to the selector. So I've got clock frequencies available all the way from 2048 Hz to just 1/4 of a Hz. But how many of those are actually useful for driving my relay computer? Well, beyond 32 Hz, the relays in the computer won't be able to mechanically operate quickly enough, so that pretty much puts a cap on the upper range. The lower end is slow enough for watching things through on the computer, and then I've also got the 4 and 8 Hz straddling the desired operating frequency of 6 Hz, giving a total of 8 options, which is also a power of 2. Funny how these things coincide, eh? So I now need to select a single output from a choice of 8 available inputs, and the CMOS 4000 series has an answer yet again. The 4512 8-channel data selector. This chip is quite straightforward in that it will pass through one of 8 possible inputs to its output based on a 3-bit selector value. Passing through the 32 Hz line coming in from the 4060 and alongside the outputs from the 4024, I get the following frequencies. By setting the 3-bit selector value accordingly, the desired frequency is selected. Rather nicely, a range of rotary switches is available that can produce this 3-bit value, giving a very nice way to turn the frequency up or down across 8 positions. Updating the circuit diagram once again, I now get the following. The lower 7 inputs to the 4512 come in from the 4024, with the 32Hz line coming in to the highest input I7. The chip enable on pin 10 is held low, and likewise with pin 15 for the output enable. The 3-bit rotary switch, shown here with 1 switch per bit, come into pins 11, 12 and 13. Interestingly here though, there's a gotcha when using the 4000 CMOS series that I've not covered yet. You must never leave an input to a CMOS chip floating. That is, neither connected to power nor to ground. This is because the input pins have a very high impedance. So high in fact that a random electrostatic charges can affect them, activating the inputs and giving unpredictable results at the outputs. And floating inputs is exactly what happens here when one of the switches is open. To work around this, I use a pull-down resistor, which will ensure the line is grounded when the switch is open. So I'm pretty much there now with just one problem left to solve, which is how to drive the relay that will drive the clock line of the computer. Now the outputs of a 4000 series CMOS chip can typically source or sink a current of around 10 mA, so shouldn't be used to drive larger loads directly. You'll be fine with an LED or similar, but for driving a relay it's best to use a transistor, and doing so gets me to the completed circuit design. Now not shown here is a protection diode over the relay coil, but to be honest I've had enough of drawing diagrams for now, so this will have to do. So then that's all the theory and design work done, but next job is to put this all together for real on a breadboard and make sure it all works in practice. And that's something I'll do in the next episode. So, thanks again for watching, and if you've made it this far, please do consider subscribing, but either way, I'll see you next time.